All right, last lesson of this year. We're talking normal distribution curves here. So many large data sets have a distribution that can be well described with what is known as the normal distribution. You'll also hear it referred to a lot as the bell curve. So this curve is seen in the accompanying handout to this lesson, so it's towards the end of this lesson. And it shows the percent of normally distributed data set that lies between half the standard deviation increments from the mean. So let's take a look at it. So if you go to that last page there, I'm going to zoom out a little bit so you can see it. As you can see, I've already started highlighting mine a little bit because that's what I do. I like to highlight. So right here, this line right here in the middle, that's your mean, always. And that's at 0 because you haven't gone anywhere with it. So your mean is always in the middle of the bell curve. Again, bell curve. Boop. So, here represents one standard deviation below the mean. This would be one above the mean. That's why this is minus, because that's indicating you're going to the left, so you're going lower. Positive, you're going to the right, higher. So one standard deviation below, one standard deviation above. So what ends up happening is if you add these percentages up here, this ends up being a total of 68.2%. So people kept doing all of these different experiments and studies, trying to figure out things, and this distribution always kept coming up. So that's why it ended up becoming the normal distribution. And what you'll end up seeing is the more studies you do to try to figure out your theory, the more and more normal-like your information will become. So with the normal distribution, 68.2% always falls within one standard deviation of the mean. So again, that's one below and one above. Always ends up being 68.2%-ish. Again, there's a little give and take with it, but generally it's that amount. So the majority of your data, more than half of your data, is going to fall within one standard deviation of the mean. So then here we got 2. So if you add up from 2 below to 2 above, that's 95.4% of your data. So pretty much all of your data is going to end up falling in that 95.4% range there. Not as common, but we do use it every once in a while. 3 below to 3 above is 99.8% of your data. So pretty much 3 standard deviations below to 3 standard deviations above, you're going to have all of your information in there. Not very much, and as you can see by the percentage, not very much falls outside of the 3 standard deviations. Only about 0.1% of the data. So if you have a number that actually falls outside of 3% or 3 standard deviations, I mean, really, even if it falls outside of 2 standard deviations, that is a statistically significant value. That is highly important and useful with whatever it is that you're dealing with. So we're going to be using this chart to figure out our numbers because all of our data is going to be normally distributed as far as we're using. So I'm going to keep flipping back to this. So, looking at exercise number 1, going back to our first page there. For a population that is normally distributed, find the percentage of the population that lies within one standard deviation of the mean. So what I'm going to do is I'm going to take my little chart, go from 1 below, add 15 plus 19.1 plus 19.1 plus 15. That's how I got my 68.2%. I already had that. 2 standard deviations of the mean. So again, that's adding them all up. Starting from here, adding every single percentage up. So that gives me 95.4. More than 3 standard deviations away from the mean. So that is beyond our 3. That's only going to happen 0.2% of the time. And then between 1 and 2 standard deviations above the mean. So that's between 1 and 2. I just added these two together, so 13.6%. That part's pretty easy. Again, you're just adding your numbers off of that bell curve that we have. So as can be easily seen from exercise 1, the majority of any normally distributed population will lie within 1 standard deviation of its mean, and the vast majority will lie within 2 standard deviations. A whole variety of problems can be solved if we know that a population is normally distributed. So, looking at Arlington High School, we got 424 juniors recently took the SAT exam. On the math portion of the exam, the mean score was 540. So that's why I wrote that there, with a standard deviation of 80. If the scores on the exam were normally distributed, answer the following questions. They wanted to know what percentage fell between 500 and 660. So what I have to figure out is where on my bell curve those two numbers are going to end up falling. So if I draw a quick little sketch, I know right there in the middle, that's my 540. Your mean is always your middle. So, again, my two numbers I'm trying to find are 500 and 660. So if I do 540 plus 80, that's going to get me to 620. So 620 is the value at 1 standard deviation above the mean. So I'm not quite there yet. I got to get to 660. So 620 to 660, though, that's only 40. So that means I'm going to go to half of a standard deviation. So I'm at 1.5 above. That's where my 660 falls. So then 500 from 540, again, that's not going to be 1 full standard deviation. That's only going to be a half of 1. So that's 500. That's at negative 0.5. So if I go back to my curve, negative 0.5 up to 1.5, add up those percentages in between those two values. So we get 62.4%. So 62.4% of the numbers are going to fall in between those. So then over here, they wanted to actually know how many students that was. So my 424 times my percentage gives me 265 students. They told me to round to the nearest whole number. So that's normal rounding rules there. Oh, excuse me. So then Evan scored a 740 on her math exam. What percentage of the students who took the exam did better than her? So if we're looking at this, wherever her 740 number is going to fall, anyone who's better than her is going to be to the right side. Worse is to the left because they got a lower score. Better is to the right. So anybody who did better than her is going to be to the right of her. Let's first figure out where she falls, though. So, going back up here to my little curve. 2 standard deviations would be a score of 700. She got 740, though. So that means she's going to be at 2.5 because I got to go up 40 more to get to her score of 740. So she's up there at 2.5 standard deviations. So they want to know how many kids did better than her, though. So if I go to my curve, she's right here at 2.5. 0.5 plus 0.1, 0.6% of students did better than she did. So there's my answer. There's my percentage, 0.6%. Let me move that out of your way. So then they want to know how many actual students is that. We know it's 0.6%, it's less than 1%. But how many actual students is that? So I multiply, and it ends up being about 3 students. Only about 3 students out of the 424 did better than Evan did. Let's take a look at the last page here. So the heights of 16-year-old teenage boys are normally distributed with a mean of 66 inches. As soon as I see that phrase, normally distributed, I'm starting to make my little curve. 66 inches right there in the middle. Standard deviation of 3 inches. So every 3 inches. Jabari is 72 inches tall. Which of the following is the closest to his height percentile rank? Now, percentile rank, we didn't talk about this too much yet, but you did talk about this last year. Percentile means your score and everybody lower than that. Percentiles are used a lot when they're measuring children. They like to measure height, weight, and head circumference to make sure that you stay in a proportional relationship there. So then they always compare you to the other children that are born on the same exact day as you. And they end up giving you a percentile rank. So, for example, my oldest daughter, her head circumference was always in the 96th percentile or 97th percentile, 98th. She was always in that range. So what that meant is 96 or 97% of the kids born on the same day as her had a head smaller than hers. That's what the percentile does, is it tells you where you are in relation to everybody else. A percentage doesn't always tell you that. A percentage just tells you how much of something you got right, whereas the percentile then ends up comparing you to something else. So they want to know what his percentile rank is. So what we have to do is we have to figure out where he falls on that normal distribution curve and then start adding up all of the percentages from the bottom. That's going to be his percentile rank. So standard deviation of 3. So one standard deviation would be 69. 2 standard deviations would be 72. So that's where he is. He is 72 inches tall. So he is at 2 standard deviations above the mean. So you got to take your curve, add up all of the percentages until you get to the 2. So that ends up giving you about the 98th percentile. I think it was like 97.9. So about the 98th percentile. So similar question here. Switching up soda cans. The amount of soda in a standard can is normally distributed with a mean of 12 ounces and a standard deviation of 0.6 ounces. If 250 soda cans were pulled by a company to check volume, how many would be expected to have less than 1.1 ounces in them? So let's first figure out where 11.1 ounces ends up falling on our normal distribution curve here. So 12.6 ounces. So that would be 11.4 is minus 1 standard deviation. It's not another 0.6 to get me to 11.1, which is where I'm trying to be. So that means it's going to be negative 1.5 is where our 11.1 is. We want to know expected to have less than the 11.1. So we're going to add up our percentages, 0.1, 0.5, 1.7, 4.4. Those are the ones that are less than our 11.1. And then we would multiply it by our 250. So here we are adding them up. So 6.7% times 250 means we have about 17 cans that we can expect are going to have less than 11.1 ounces of soda in them. Okay. Biologists are studying the weights of red king crabs in the Alaskan waters. They sampled 16 crabs and compiled their weights in pounds as shown below. So there's the weights of the 16 Alaskan king crabs that they were sampling. Part A, find the mean and the standard deviation of the sample of crabs. Pause, type it in your calculator, try to find it yourself, see if it matches. So you should get 12.6 and 1.5. Why does this sample indicate that the population would be well modeled using a normal distribution? So, 11.1 to 14.1. That's minus 1 standard deviation and plus 1 standard deviation. So I went down 1, I went up 1. And then I counted. I sorted my list and I counted. And there was 11 out of the 16 that fell in that range, which ends up being 68.75%, which is pretty darn close to a normal distribution curve. So that is why it's going to end up working. So part C. Assuming your mean and standard deviation, part A, apply to a normally distributed population of crabs. what percent would fall between 9.6 and 15.6 pounds? So 9.6, 15.6, those are 2 standard deviations. So I'm adding 95.4, 2 standard deviations above and below. So they must throw back anything that weighs below 10.4 pounds. So on my normal distribution curve, 12.6, 11.1, so then a half, minus 1.5 standard deviations. That's where a 10.4 would fall. So that's going to be 6.7% of them are going to get thrown back because they'll be less than 1.5 standard deviations below the mean.